everybody. I appreciate you taking the time to join us today. For those of you guys who might not know me, my name is Greg Everett. I'm the Vice President Operations over here at Sierra Dental Tool. You know, if you're not familiar with Sierra, our claim to fame is really high quality milling tools for all the CAD/CAM machines. We've been producing those tools for the better part of a decade now, and you know, our core mission in the industry is to help laboratories become more efficient and you know, save money on their bottom line. So this webinar, we're going to go in and do a little bit of a deep dive on what tooling is and how it affects the digital workflow, and we'll go into how you know, how it actually directly affects your production, down to some kind of nitty-gritty technical tool theory for the nerds that are out there, and then we'll go into some of the common milling issues that you might see pop up. At the end, we'll kind of go through what Sierra has as far as offerings for dental labs and how to make the best use of those. Then if I don't ramble too much, we'll have some time for Q&A at the end. So with that, I'll start diving into it. All right. So the first thing that I like to mention in these is, you know, when you're doing digital production in the lab, especially with milling machines, the entire workflow it's basically like a chain. You know, it's step 1, step 2, step 3, step 4, and each one of those steps has a you know, a component or a piece of equipment that's linked with that. And you know, a lot of times you'll see somebody focus down on just one piece of that chain, and you know, it'll be like, well, do I have the best scanner or do I have the best mill? And the key thing is to think about it as one big entity, and consider the strength of each chain as you go, as each of those links as you go through it. You know, as you design your workflow, you know, some of those links you want to have redundancy in, and some of them they're not necessarily cost effective, you know, to double up on. So when you're designing a good CAD/CAM digital workflow, the first thing we care about is the business case, right? So it needs to be cost effective. It also needs to be reliable. We can't have people spending hours and hours on the phone with tech support. And then we want to create consistent and quality results. You know, if in order to be profitable in especially during these times, you have to know what you're getting out the other end. And so I hope that, you know, this messaging will help, you know, somebody pick up a tip or something that'll help them achieve those things. Some of the components of those of a good workflow is, first off, people. You know, invest in your people. Make sure that your relationships with your vendors, with your clients, and everything are strong. You know, as I'm sure many of you guys know, this is a very relational business that we're in. And you know, with the race to the bottom on certain restorations that labs are working against, you know, you're not selling a crown, you're selling a relationship, and you're selling that support. And then, you know, you want to invest in good equipment. You know, I always encourage you to ask your friends, you know, if you're in the market for something, ask your friends what they're using. Find 2 or 3 people who are using a piece of equipment that you're looking at. Make sure that they're happy with it, or see what their issues have been. And then lastly, don't overlook the consumables. You know, your materials, they play a big role in your cost. You know, if you can use materials more efficiently, your bottom line will be you know, more healthy. And then under that consumable category is where the focus of this presentation is, and that's your tooling. So that's when Sierra got into the industry. We identified the tooling as the weakest link in that digital, milling production chain. And the status quo in 2007 when we came into the industry was, tooling was it was a fire and forget sort of thing. A carbide tool, like let's say on a 3M lava machine, which were popular during that time. That tool would cost around $50, and you'd get one cycle through the machine. And so the tooling cost was a huge proportion of the cost of the unit production, and we strive to solve that problem and to make it more efficient for the lab. So some of the things you want to keep in mind when you're thinking about tooling is that everything that you do in your production, from pouring the impression to scanning to designing and nesting, it all ends at the tool, because the tool is that last point of contact. It's literally in contact with your restoration, and it makes all the difference in the world in regards to your efficiency and your results that you get out the door. So now we'll dive into some detail on how that actually occurs. First off, another way to reiterate it is that tooling, it literally is the business end of your process. So it directly affects your quality, and that has to do with your marginal integrity, your fit, your finish, everything that goes into a crown that we care about. It also directly affects your success rate. A tool that's bad will cause you to have more remakes, which is more labor on that side, more material, more wear and tear on the machine. And so the tooling aspect of the production is quite important. So a little bit on tool quality and how it affects the quality of the machined unit that you're putting out the door is, so if you think about the shape of a tool and as it's cutting, that shape is directly imparted to the surface of your crown. And so, like, one of the examples I use is that if you're using a tool that may have been sourced like on eBay or something like that, that tool might say 1 millimeter on the package, but it might actually be 1.05 or 1.1 millimeters in diameter. And if your software is expecting it to be 1 millimeter, but the tool is actually undersized or oversized, your fits will go out the window. They're either going to be tight or they're going to be loose, and it ends up being a huge headache on how do we figure out how to what's causing this issue. And a lot of times people think, oh, there's no way it's a tool. A tool is a tool. A tool is not a tool, as you'll see as we progress through this. I really like this GIF here. You can kind of see the way that a cutting edge cleaves through material. And as it's moving through the material, it's kind of like the bow of a boat. It's just splitting the material and shaping it. So onto the next here. When you're looking at the cost of a tool, don't just think about the how much it costs you. Also think about what's the cost of that remake that was caused by a cheaper tool. What's the cost of your labor? What's the cost of the wear and tear on the machine? Using a quality tool will inevitably result in less remakes and just less overall digital headache. So there's basically one key metric that you want to look at when you're looking at tooling in your workflow, and that is your cost per unit of production. Because as a dental lab, I get paid on the unit. I know they're all custom and they're all a little bit different. But what I care about is, okay, how much did the material cost me? How much did the labor and everything? How do I boil all that down into one cost of cost per unit? And you can do that with your tooling too. But you have to track a couple of things. You have to track your tooling usage, and you have to track your milled unit output. And you run the math, figure out how many dollars you're spending per unit of production. And what you'll find is that if you spend a little bit more upfront on a really high quality tool, your per unit production will just go through the floor. For example, I brought up that 3M tool that we basically in 2007, that was one of our focuses, was the 3M machine. And you know, at $50, you know, you'd get 40 or 50 units out of that single tool. So your per unit cost per tool was, you know, around $1, and you multiply that times a 3-tool system, and you've got a $3 cost in your unit. Now on the other side, if you're using a tool that's like for instance our diamond tool, which will actually 10x that yield or better, you know, many of our labs have you know, they're running cost per units down below 15 cents, and so it's really very effective. And of course, depending on the volume you're putting through the lab, utilizing a high quality tool could mean $15,000 in savings over the course of a year or more. So to tie that point up, you know, let tooling be the strongest link of your workflow. It should be something you can rely on, and make sure you're getting those repeatable results. And you know, that's what we try to deliver over here at Sierra. So now I'll jump in a little bit onto the technical side of things. And so dental labs, in our experience, are not machinists. You know, we basically want to push a button and get a crown and have it be reliable and repeatable. You know, many labs, the vast majority of labs, don't really have time for R&D. They basically want a solution that they can rely on, and that's what we try to deliver. So when you're looking at how a tool actually affects your workflow, you're going to be concerned about getting the best life out of that tool. And so there are essentially 5 things that will affect your tool life. It's the top 5 things. There's actually 30 things, but we're not going to go that deep into it on this one. So we'll talk a little bit on each 5 of these, go through calibration strategies, run out, which is a huge one, and then material type, and how to handle and store a tool. So on with that, let's jump right into it. The first thing that is good to kind of drive a corollary to is a milling tool is a good comparison is a milling tool to a car tire. So you know, there's a huge variance of different brands and you know, qualities that you can do when you go out and purchase tires for your car. Now, depending on how you run those tires, that's gonna decide how much life you get and how many miles you get out of the tire. So you know, I typically, you know, my hypothetical Porsche that I don't really have, I'm not going to go put Walmart tires on it. I'm going to put some good high performance tires on it and make sure that it's aligned and everything's good, so I get the most bang for my buck. And milling tools are exactly the same thing. So the things that decide what you get with a milling tool are the you know, it's very susceptible to the environment that it's subjected to. And as a lab, there's some of those things that we can control, and then there's some of those things that we can control. Mainly, your milling parameters are going to decide the wear rate of your tool, and then we're going to talk about you know, how rigid your machine is, how much spindle power output it has, and I'll go a little more into detail here on the next couple of slides. But first off, we'll start with the things that the lab does have control on, and the main thing is your maintenance and calibration on the milling machine. You know, I've got 10 years of experience in a dental lab, and I know how how it can kind of, you can kind of neglect things sometimes, because the number one focus a lot of times is, hey, we got to get this unit out the door. You know, we got to get it to the doctor. It's a rush case, et cetera, et cetera. We'll just skip the calibration. But if you look at, if you back away again and look at the workflow as a chain, like I like to put out there, if you make the commitment to put to calibrate regularly, your overall digital headache will go down. And so what we recommend is, first off, read the documentation that came with your mill. You know, the manufacturers of the mills do an awful lot of work to create that. And time and time again, I go into a lab and I'll find that the documentation is still mint condition, and it's nice little, you know, cellophane cover, like a Spider-Man 1 issue. You know, we don't want to open it. It's going to be worth something someday. But, you know, just take that thing out and read it cover to cover, or the person in charge of running your mill should be reading it cover to cover and really understand it. And put a policy in place to calibrate based on what that documentation says. And generally, calibration is based on you know, the interval of how many units you've run. So, you know, if you're running, you know, for instance, if you're running like 200 units a week, it might be good to do a calibration weekly, or something along those lines. But just take a look at the documentation, and that'll usually answer that question for you. Now, the reason calibration is necessary on a lot of machines is we get a couple of things happening in the lab. First, there's a thermal variance. So as you know, as the ambient temperature in the laboratory goes back and forth, the machine can grow and shrink. And you know, that's a dimensional change that's not, it's very small, but it's not insignificant, you know, when we're talking about trying to achieve micron accuracy with some of these machines. And then the more you mill, the more you need to calibrate. So a lot of the machines have open loop control systems, which means that they only know where they are in space based on 0. And so when the machine is told to go from 0 to 20 and back and forth and back and forth, the mill doesn't actually know, it can't account for any sort of mechanical backlash or play that's in the axis. And so when after you've run it for like a week, it's done 1,000 of those cycles. Every time there's a little bit of an error, it stacks. So now when you tell it to go to 20, it might go to 20.1, but it still thinks it's at 20. And so as you machine more, you need more calibration. All right, so I could probably do a whole thing on that, but let's move into the next one here. I'm certain that if you're milling, you know what a milling strategy is. If you don't, a milling strategy is it's exactly what that is. It's the strategic order of operations that the machine takes in order to create your crown. So in the simplest terms, you know, you're going to start with a big tool. You're going to remove 80% of the material, and then we're going to do a semi-finishing or a finishing operation with the next tool down, which is usually like a 1 millimeter. And then after that, you're going to go in and detail it with a 0.6 or maybe even a 0.3 millimeter tool in some applications. So it's like a 1, 2, 3 sort of step. Now, on the back end, these strategies can get really, really complicated because there's different variables for material, for the specific machines, for the tooling, of course, and all of that is managed by on the back end by your tooling manufacturer, which would be us, your cam supplier, which would be one of a couple of different ones that are available, and the distributor of your machine. And those three people really need to be tightly linked and in constant communication in order to maintain the development and the validation of milling strategies. Because for any of you guys who've been in this industry more than a couple of years, it's super dynamic. I mean, we're getting new materials, we're getting new processes. It seems like, you know, every time I open up my LMT magazine, there's something new in there. And so the strategies have to keep up with that, and they have to be continually tested and validated. So definitely don't overlook the strategy as important. And you know, make sure that your strategies match your material and your tooling. A lot of the support things that come up on that trickle down to our end is actually, I would say 90% of them are based in an outdated strategy. You know, the laboratory didn't update their software in a couple of years, and you know, they've been dealing with certain issues like broken tools or what have you. And you know, we'll sign on and look and think, oh well, this was updated you know 12 months ago, and the issue was solved. Here, well, let's fix it while we're in here. But the update may have kept you from having that issue in the first place. So we'll move on here. The other thing that strategies are very specifically matched to is the actual material. Now, there are different versions of you know, there's 50 different types of zirconia out there. There's you know, dozens of types of PMMA and wax and all these different materials that we mill in the lab. And the strategies are designed to basically like the least common denominator. They're designed to work for zirconia as a category, but they're constantly being updated. So like, let's say that we have a new zirconia come out on the market that you know, is becoming more prevalent, and it may be a little bit different to machine than the majority of zirconias that were previously out there. That would merit the need for a strategy change, which would be you know, we might change one setting here, one setting there, so that people running the strategy will be able to machine this new material without having an issue. One of the things I recommend to people, if you want to understand this kind of machinability, is you know, when you're working with a material like say zirconia in the green state, one brand, if you cut a sprue on one brand versus another brand, you can literally feel the difference in the way those things cut. And so take that experience and kind of that'll help you visualize the importance of updated and validated strategies. And then one other point on this is with the increasing availability of different materials, specifically for like removables and such, a lot of those materials have different thermal characteristics in the way they machine. And you know, a lot of times we'll see somebody using a new material with an old strategy, and they'll get material build up on the tool because it melted it. All that is it's a strategy setting that needs to be balanced for the material. So that's enough of a ramble on materials and strategy. Now we'll get into the main killer of tools, and that is runout. Excuse me. So many labs really aren't necessarily familiar with the concept of runout, but it's pretty simple. It's basically any degree or any deviation of the tool from the center line of the spindle. So as it's running, if it's wobbling at all at the tool's tip, it's running out. Now every machine, even the most expensive multi-million-dollar aerospace grade CNC machines, have runout. There's no such thing as zero runout. But what we want to do is try to control it. And the reason why it's important is because as a tool's wobbling, even if it's microns, it's creating a non-uniform load on the tool. And a good illustration of this might be, let's say you've got, let's say you're disking like an embrasure or something on an anterior case. You know, that tool wants to cut at a certain rate. You want to let the tool do the work. If you force a disc into your embrasure, it'll kick back. You might bend the disc. You might build, you know, you can always hear in the lab that like zing pop noise when somebody does that. And so it's the same thing with the milling machine. It's really, that tool is really experiencing the same sort of thing as your hand tools are. And so when it's running out, it's getting unloaded and unloaded and reloaded and unloaded and unloaded constantly. And so it, you know, your tool wear goes exponentially with runout. So a perfectly tuned machine, you know, you might get 1,000 units, but if you're running out a couple microns, you might get, you know, 800 units. If you're running out, you know, if you triple the run out, now you might get 400 units. And so we really want to do everything we can to do to control that. One little side note here, this little GIF I have is actually a good illustration of differential load. This is the Tacoma Narrows Bridge that was built in Washington, I think in the like 40s or 50s. And it was a suspension bridge, and they didn't take into account the wind loads. And so as this thing, as it got windy, it created this feedback loop where the structure kept getting worse and worse and worse. And eventually this bridge collapsed, and it was a complete failure because the engineers didn't take into account that aspect of the design. So let's see, I love stuff like that, so I like to work it into my presentations. So this is actually a really good example under magnification of a tool that was in a pretty severe runout situation. And you can see that it actually has favored one of the cutting edges over the other and worn it at a much higher rate. So this tool is probably still cutting, but it's near the end of its life, and it's been drastically reduced. So as a laboratory, there are a couple of things that we can do to control runout. One is the collet maintenance. And for those of you who don't know, might not know what the collet is, if you watch your machine go and grab a tool, the collet is a little thing that sticks out. It's basically the chuck of your handpiece, sticks out, grabs the tool. That collet is, it's responsible for centering the tool in the spindle. And it requires maintenance. Every single one of the machines that you guys have, if you read your book, it's going to have a section on collet maintenance. And what we like to see is we like to see collets surgically clean, inside and out, and not showing any signs of wear. You know, if you're showing some signs of wear and you've got a reduced tool life, first thing I would do is look at the collet. And so in this GIF, you can actually see about mid-center mass, you can see a wear facet growing on this tapered area. And this collet isn't bad yet, but it's getting there. It's also dirty. So when I pull a collet out of a machine, you know what? Really the best way to do it is, you know, if you got a steamer, go in, lay into it with a steamer inside and out, and then you know you can wipe it down with some isopropyl alcohol afterwards. Make sure it's thoroughly dry so it doesn't rust, and then replace it. Of course, go back to your documentation on exactly how to do that. So along with your calibration, you should also have a policy in place on collet maintenance. In fact, it's good practice to maintenance the collet when you do the calibration. You know, you might as well just hit all of it at the same time. And then the next thing, which we really can't directly control as a laboratory, but it helps to really be aware of, is, you know, the spindle itself is a high precision instrument, and you know usually they're running loaded under, you know, like 30,000 RPM, 25,000 RPM. Some of the crazy ones will go up to 60,000 RPM, and there's a lot of wear and tear on the bearings inside that spindle. And so most spindles will have a published hour rating on the spindle, and you basically you need to be aware that they wear out, and you will have to replace it eventually. So if you've done a collet, but you've got a lot of hours on the spindle, but you're still getting kind of unsatisfactory results, it might be time to do a spindle. So as those bearings wear, as I'm sure you can imagine, they end up with more play, and you end up with more run out as the wear progresses. And then finally, when it comes down to the total indicated run out of of that system, which is the spindle, the collet, and the tool. If you were to measure the run out at the tip of the tool, which is where we care about it, the other driver of that is the accuracy of the tool itself. You know, when you grind the cutting edges onto a blank of a tool, that cutting edge has to be perfectly concentric with the shank of the tool in order to keep the tool from introducing run out into that system. And so everything that we make, doesn't matter what the tool is, everything's ground to an aerospace tolerance. Everything is as concentric as it's possible to get. And we've looked at other tools that are on the market and analyzed them, and I can tell you that that's not necessarily true for everything. So important things on run out, keep an eye on it. And finally, well, not finally, I think this is second to last here, material evacuation. So as your machine's cutting, that waste material, it's very important to get it out as fast as possible. And the reason you want it out as fast as possible, because if the tool comes around again and that material is still there, it's going to cut the material again. Especially with a material like zirconia, where it creates a powder which is abrasive. And so if you look at your machine and it's sitting there spending a bunch of time in a big pile of powder, take a look at your suction unit and take a look at your air pressure. Make sure those are dead nuts on spec to your machine documentation. You know, if your air compressor isn't up to the task, you know, it might be good to invest in a more powerful unit, because that recutting is it creates a significant amount of tool air and tool wear, which can negatively affect the result you get off the machine. So what you want to look at is your air pressure, your suction, and to make sure that your air is actually aimed correctly. And for those mills that you can aim the air, the easiest way to do it is to take like a little strip of paper or something and stick it into the air stream, so you can visualize where it is, and it should be pointed right at the tip of the tool. So on with that. The next kind of easiest way that you can reduce the life or the yield of your tool unfortunately, comes from human error. It comes from handling, you know, proper handling and storage of the tool. So all the milling tools that we produce are made out of a material called tungsten carbide, which is it's a material that's used across all industries for machining. And it's a very, very hard material. And actually, interesting note, it's actually a sintered material. It's very similar to zirconia. It's pressed with a binder and then sintered. Kind of neat little piece of little factoid there. But the point is that the geometry of the tool is very precise. And if it's loaded in a direction that it's not designed to be loaded in, it can have an issue. You can create damage on the cutting edge pretty easily. And so there's a couple of points. What you want to do is you want to make sure you keep them clean. And if you're storing them, store them in your original little plastic sleeve that it came in, because that's going to keep it from rolling around in a drawer or maybe coming in contact with something else like another tool. Or an instrument or something like that. And so if you take it out of the machine, always keep these and put them back in there. And make sure that you're careful with the way that you install the tool. One of the easy ways to chip or damage a cutting edge is when you're putting it into the tool holder and slamming it into that metal inadvertently. And you can actually see here in the upper right picture, this is a tool that under magnification, you can actually see some brass transfer that's gotten deposited on the tool from it hitting the brass tool holder on installation. And so with that, I'll end that little rant on this example And so this is a tool that we took as part of a blog post on our blog site, We Team Up, and in a controlled environment, impacted it onto another tool. And we did it with a very, very small amount of force. In fact, the machine was calibrated to the amount of force it takes to, just tap a pencil lead on the table and chip the lead. And so with a direct impact, we were able to create this sort of feature in the tool. Now, this tool will still work, but it's really not going to work very long. We've cut the life of the tool by 80%. And so it's really easy to avoid this just by being careful with it and treating it like a precision instrument. Okay, so let's see, how am I doing on time? Ooh, yes, I like to rant, don't I? Okay, we'll go through some of the common milling issues that we see in the lab and what to check. The main theme here with diagnosing anything in the lab, whether it's a mill or a scanner or whatever, is start with the most obvious and the cheapest thing first. And usually you can apply Occam's razor. It's usually the simplest thing that's causing your issue. So I think I've got 4 or 5 examples of milling issues. We'll run through these. So the biggest one that we see in the lab is a chipped margin. And so margins can chip for a variety of reasons, but usually when I'm on the phone with somebody who's having chipped margins, it's the first thing I check is a CAD settings. That's free. It only takes 5 minutes. Let's make sure that we're cutting a margin at 200 microns. That's the bread and butter setting. 200 microns is if you're cutting at 200 microns, you will not see margin offset related chipping. Now, a lot of labs like to go lower on that, 150, 50, what have you. But if you're going to do that, just be aware that you're increasing the risk of chips. And your collet and run out, which I talked very specifically on, your calibration, and those all affect the performance of the tool. And eventually, if you're cutting with a worn out tool, it will chip the margins. And then another thing that's interesting to point out, which is actually the first point on my list here, is the roughing tool and the finishing tool can both equally create chipped margins. So when you look at a chip margin, you might intuitively think, oh, well, it has to be that finishing tool, it has to be the 1 millimeter, because that's the tool that's putting, it's actually doing the finishing. So that's the one that's doing the chipping. However, that's not always the case, because if you're roughing with a big tool, the way that zirconia machines is that if that big tool is dull, it can actually traumatize and microfracture the zirconia and cause a chip further down the line of the machining process. So if you're chipping, definitely look at both of those tools. Surface quality. Surface quality is a big one. The two biggest effectors of surface quality are strategy. Is that set right? Is that updated? And the mechanical reproduction of the machine. Is the machine doing what it's told? Which is usually 90% of the time calibration. Fits. So if it doesn't fit, probably doesn't fit for a reason. And the first question that you want to ask yourself is, where does it not fit? For instance, if you have an anterior case that's not fitting in a sharp area, that's probably a CAD setting. That's probably your machining tolerance for the tool. Or you might have a scaling factor issue if the entire thing is tight. So ask yourself where it doesn't fit, and that'll help you visualize where the issue might come in. And then you, again, start with the cheapest stuff. Start with settings, start with calibration, stuff you can handle in the lab. And eventually, if you go down that route and then find out that you have a machine issue or you need a spindle or something like that, at least you check those other ones off the box. All right, so broken tools. Broken tools, they happen, but 99% of the time, a broken tool is a symptom of a wider issue. The majority of broken tools are caused by mismatched strategies, or user error, like you loaded a 1 millimeter in the 2 millimeter slot, or perhaps you set up your program for a 14 millimeter puck, but you loaded an 18 millimeter puck. Long story short, tools don't break unless they're broken, and there's a reason why you're getting a broken tool. So do not deal with broken tools. Don't write that off as, oh well, they break occasionally. If you're getting broken tools on a regular basis, call into support and figure it out, because there's a solution to it. All right, let's see if I can get through the rest of this thing. So, Sierra, over the years, we started in the industry because we saw the need for a better tooling solution. And so over the years, we've been constantly developing, and current state of business, we have a solution for nearly every single milling machine that's on the market, and as well as every material that laboratories process in the lab. So I'll just quickly go through a couple of those. The one I'll spend the most time on here is our Diamond tool. And this is our flagship product. This is the one that we that really does the job for laboratories. And like I said before, we're 10xing or better the life of a comparatively positioned carbide tool. Your overall result is less cost per unit, sub 15 cent per unit, and repeatability. Those are the things we care about. So I'm also wanting to stress on the point that yes, there are other tools on the market that are marketed as Diamond tools. Unfortunately, that's a little bit of a buyer beware sort of situation, because Diamond is not all the same. There's as much variance in the way you diamond coat a tool as there is in the way that you stack a zirconia crown or a PFM. There's so many different little nuances and variables that have to be controlled in order to get a good result. A company that's good at coating industrial parts like brackets or whatever is not good at coating tools. And so, we've spent a lot in R&D and development to create a coating process that works extremely well, specifically for these micro tools that we're marketing in the dental industry. And the thing you want to look at is, is it a true CVD tool? CVD means chemical vapor deposition, which quickly, it's basically there's a reactor, the tool is inside, and an atmosphere of CH4, which is methane, it's 4 carbons, is introduced into the reactor under a real high temperature, which breaks apart that molecule, and then the carbon actually precipitates in the chamber and crystallizes directly onto the tool surface. And I'm losing my voice here. Excuse me. So as you build that, you have to control the thickness, the time, the size of the crystal. There's 50 different variables that if one goes out the window, the quality and the result can be different. So at Sierra, we're very good at coding. Keep that in mind. Okay, so we also like to prove what we say. And so, when we market a tool that says you get 1,000 units, then we want to prove it. So we've actually run this study in SageMax Zirconia with our NanoDye product, and went through and documented the tool wear over every 50 units. So we milled 1,000 units, the same puck, kind of over and over again, and in detail documented everything. So this is an image of the puck, and an interesting thing to point out is the breakdown of machining time. And when we're talking about that step, that 1, 2, 3 steps, so the 2 millimeter in this exact program is running 1.1 0.61 hours, and it does this many millimeters of linear tool path. So if you were making the tool go straight, that's how far it went. And then as you go, let's go back one. As you go through it, you're seeing that we're spending the vast majority of the time on the 1 millimeter and not that much time at all on the 0.6. And so the tools actually wear in that ratio. Your 1 millimeter, you're going to use a lot more of those tools. Shoot, another savings on that you can take advantage of at the lab is replace the tools on an individual basis. A lot of times your 1 millimeter will wear out because it runs most, and your 2 and your 0.6 are perfectly fine. So there's a good takeaway for you, hopefully. So here are the results. So this is what the tool looks like new under magnification. You can see the kind of the crystallized structure of that diamond coating. And here we are midway through, and you can see a very small wear facet developing on the tip of the tool, on the cutting, kind of the apex of the ball there. Tool is still perfectly fine. We're getting very good results. And then finally, at 1,000 units, you can see that wear facet has grown probably about double to the 500 unit mark. And this is where we stopped the test, but this tool was not near its end of its life. You know, in our experience, this one probably would have gone out to 1,500. And of course, this is done it's basically done in a brand new machine. Everything's calibrated, everything's perfect. Which is why you want to look at those things, because if you balance all that, you're going to get the best use out of your tooling. And just for those of you guys who want to know what 1,000 units looks like, it's actually a little smaller than you might think. So this is kind of a fun little photo to look at. 1,000 units, 25 per puck times 40. Okay, that's the nano die. We'll see. I've got about 5-10 more minutes, so let me just shuffle through here. Our razor sharp, which is for wax and PMMA. The key differentiator there is the very, very sharp cutting edge. We get much better surface finishes and much longer life compared to other carbide tools, which is of course important when you're talking about time spent post-processing. If you're machining metal, we've also got you covered. Our Tyco tool line uses a really, really high-tech, cool thermal coating, which actually prefers to run hot. So these tools last a lot longer than what you see out there offered by the OEMs. And finally, we've got your lithium disilicates and composites covered. You know, we've got a line of composite tools that do a very good job of machining those materials as well. So I've got one other little section that I want to share with you guys. Let's see if I can rant through this pretty quick here. And that is one of our recent innovations over at Sierra, and that's our focus down on removables. You know, many labs are probably aware that removables is the growth area in our industry. You know, you've got the baby boomer demographic requiring more of this sort of a restoration. And so, you know, the laboratories that figure out how to produce a digital removable you know, they're going to be ahead of the curve. And so when we looked at this, you know, in collaboration, by the way, with our friends in the industry, and Zahn, Meyerson, Sim Systems, we all kind of came together around this and created this solution. So the existing situation was it's not cost effective to machine plastic because my opportunity cost basically is 3 full contours per hour, or I could do 1 denture in 5 or 6 hours. And the amount of money I can sell either of those for, the math just doesn't work. And so there's a growing demand, but how do we make it cost effective? And the key to that is getting your process times down. So if we can cut a significant amount of time out of the processing, we can change that ratio, right, and make it much more cost effective than it was before. So again, as a collaborative effort, we developed a strategy for the Roland system that utilizes this new tool geometry for cutting plastics. And we reduce the roughing stage extremely. We'll take, for example, a typical denture might take, with a 2 millimeter, it might take 2 hours, 2 hours and 20 minutes just to rough it, and then an additional 2 hours to finish it. So you're in that 4, 5, 6 hour range, depending on the design. With this solution, we rough that same denture in about 20 to 30 minutes. And so the overall time savings on the process is about 40, 50%, which again, makes it more cost effective for you. So I've got a couple of examples to show you guys. This is an RPD that's machined out of Meyerson's material, VisiClear, done in 90 minutes. Pretty impressive. And by the way, that's done with photo credit Mark Rosenberg from Pride in California. Thanks, Mark, if you're watching. And then denture bases. So this is a full denture base being roughed here in the video. That this denture was roughed in 28 minutes, and the full process time was right around 2.5 hours. In fact, I have it here. I'll show you. And by the way, the result. This is just off the mill. This is not polished or post-processed at all. The teeth are just glued in, and that's it. So those are the surface finishes that you can get using a razor sharp tool. So again, you know what? If I were finishing this in the lab, I'd fit it and I'd do a high shine on it, and it'd be out the door. The machine did 80% of the work for me. So very, very, very cool and scalable. So on with that, let's see. That's enough of the video, I think. So the tool is, long story short on that thing, is it reduces material really fast, and we take those process times down. It's available on Rollins, so if you're using Rollins, your item code with Zahn is 221-0076, which I think this presentation will go out to everybody who attended the webinar, so you'll have this as a reference point. And then quickly, I wanted to share our resource that we've put together along with other kind of team players here in the industry, called We Team Up, and it's our blog site. It's free information, mainly around milling and digital production. We're always adding to it. You can find that at weteamup-dental.com, which the URL is on the end page here. Very good resource if you're looking to pick up some knowledge. And as a last thing here, we're running a promo for this webinar, and some of you might know that we've been putting together a new loyalty kind of program, and the first phase of that is going to be this promo here, and we're extending out the first tier pricing to everybody through July 3rd, and so definitely take this down. It's a significant savings. Use this GHP promo code if you're buying some tools from your rep, and they can give you the special loyalty pricing. Highly encourage you to do that, and of course, it might be a good time to stock up for those of you guys who are getting prepped for the deluge of work that's probably been backed up in these last couple of months. So with that, I hope that I've added some value and help somebody out. That's the whole idea here. If you have any questions, let's see. I'm not sure if any have been brought in or not, but again, you can always reach me directly, either on the phone or by email. And of course, check out the two websites if you want to know about tooling. Go to our tooling website if you want to know about production. We Team Up's a great resource. And so, Caitlin, did we have any questions come in that we wanted to address, or how are we looking on that? I don't have visibility.
Thanks, Greg. We just had one question come in here.
Sure.
2 milliliter versus 1 millimeter tools, which one is more effective for margin chipping?
So it's let's say that they're both, if it depends on the situation. You can have a brand new 1 millimeter tool and a highly worn 2 millimeter tool and chip margins, and you can also have it the other way around. The point of what I was trying to put out there is that don't overlook the 2 millimeter tool, because it can also cause chipping. And so if that one is worn, or it's at the end of its, on a roll, and if it's out over 90 hours or 100 hours, you might want to look at that thing. And so just don't overlook both of those tools in terms of chipping. Hope that answers. Or was that the only one?
And it looks like we had one more come in just now. Can I use razor sharp tools for zirconia?
Oh, excellent question. So from a profile standpoint, the razor sharp tools and the diamond tools are dimensionally the same. So you can use them in zirconia. You're not going to get the drastic benefits of diamond, although we use a really dense tungsten carbide grade in those tools, in addition with our dental specific cutting geometry, and the razor sharp in zirconia will actually yield 2 or 3 times the units than a typical uncoated tool. So the answer to that is yes. You can do it selectively. Typically, like for instance, that test that I illustrated with the diamond tools, we also did that in zirconia with razor sharp, and yielded about 175 to 200 units for the tool set. So you can definitely do it. If you're not doing that much production, it might work for you to do that. So yeah, short answer, yes.
Awesome. All right. Thanks so much, Greg. Yeah, that covers all the questions that came in.
Hey, fantastic. I'm glad we had some questions. It's always fun at the end when there's no questions at all. I don't know if that means if I did a good job or a bad job. Who knows?
Well, actually, with 1 minute to spare, we did have one more just pop in. Do you suggest changing 2 millimeter and 1 millimeter after milling 200 units, or can we keep the 1 millimeter?
So usually in that situation, the 2 millimeter is still fine. It's still going to keep running. You could probably run the 2 millimeter out to 250, 275. I think this is the same person asking me the question. I would encourage you to give me a call, and maybe we can set up a TeamViewer lesson on how to analyze tools under a microscope. I'm happy to show you how to do that and determine whether the tool has reached the end of its life or not.
Great.
In fact, that offer goes out to anybody. If you guys want that piece of information, feel free to reach out. We'll do it.
Perfect. Well, thanks so much for your time this afternoon, Greg.
Hey, thank you. Appreciate it, Caitlin. You have a good one.
You too. Everyone have a great day.